Welcome to Microlecture 34 on Carbocation Intermediates, their stabilities, and ranking the stabilities of alkene compounds. Okay, so first let's talk about carbocation intermediates. These are very, very common intermediates, and we're going to see a lot of them. So the carbocation has sp2 hybridization. So if we're thinking about what the carbocation looks like, if I can kind of make this larger and kind of turn it on its side, you see that it's flat. It's got three regions of electron density around it. And so that's how I know it's sp2 hybridized. And being sp2 hybridized, it has an empty p orbital. All right, so there's its empty p orbital. And so that's just the nature of a carbocation. We know it's flat, we know it has an empty p orbital, and we can start thinking about relative stabilities of carbocations. It turns out you can have like 3 R groups around a carbocation, and we would call that tertiary. We could have just 2 R groups and a hydrogen atom, and that would be secondary. And we could also have primary, so 1 R group on there, and we could have just all 3 groups be hydrogen atoms, and that would be a methyl. So primary and methyl. Well, as we move toward the right here, these become less and less stable. In fact, primary and methyl pretty much never form. Okay, so really we'll only see tertiary and secondary carbocations. And what makes them more stable is, well, if I go back up to my drawing of the empty p orbital, and I draw in one of the many hydrogen atoms that's sitting there, we understand that there's that one, there's this one, there's this one, okay, and they're also on the other 2 methyl groups. Any one of those sigma bonds is actually quite electron rich. And so we're talking about this carbon-hydrogen sigma bond that is that's on the carbon that is adjacent to the carbocation carbon, and that electron density from the sigma bond kind of satisfies the empty p orbital of the carbocation, and so for that reason, having more R groups or more carbon-carbon and carbon-hydrogen bonds adjacent to the carbocation carbon is going to make it more stable. Okay, so that is why more R groups on the carbocation makes it more stable. The next consideration is resonance, and it's something that we're very familiar with by now. So I could draw you a couple of examples here, but I'm pretty sure that you would be very confident seeing that that structure that I've just drawn has resonance stability. It exhibits resonance, whereas this carbocation does not. Okay, and so we're pretty comfortable with resonance as an argument for stability by now. And the inductive effect is also something that we've seen quite a bit of. So, for example, this carbocation here is destabilized relative to something that doesn't have the electronegative atom on the carbon adjacent to the carbocation. Okay, in one case, we've got the chlorine atom pulling electron density away, forcing 2 positive charges next to each other. And in this case, we don't have that, right? So I'll go ahead and go back up here, and I'll put a box around this one, and I'll put a box around this one, indicating that this is more stable due to resonance, and this one is more stable because of the inductive effect. All right, and then I wanted to talk about alkenes. So the stability of carbocations kind of parallels the stability of alkenes, it turns out. So as we add more and more R groups to a carbon-carbon double bond, we're going to gain stability. So we could think about having just one R group on an alkene. We could think about having 2 R groups. We could think about having 3 R groups, and then we could think about having 4. So the level of substitution on these are mono, di, tri, and tetra substituted. So we would say mono substituted, di substituted, so on and so forth. And it turns out that the more R groups that you have, the more stable the alkene. Another consideration to make when we're talking about alkenes is stereochemistry, and this goes along with the E and Z designation of carbon-carbon double bonds that we talked about in a previous video. So we could think about our double bond carbon atom as looking something like this versus maybe looking something like this. Okay, so let's compare the two and think about stabilities. We've got, on the left-hand side, we've got the higher priority group as being the ethyl, lower as the methyl. On the right-hand side, we've got the higher priority as the isopropyl, and the lower is a hydrogen atom. And so we can see that the higher priority groups are on the opposite side of the carbon-carbon double bond. This is favorable because of sterics. So there's less sterics in this situation than there is going to be when the high priority groups are on the same face of the double bond. So just for comparison, I did that over here, so you can see the high priority groups are on the same face, the low priority groups are on the same face, and having those large bulky groups next to each other is going to create more sterics and higher energy. Basically the hydrogen atoms that are coming off of these alkyl chains are bumping into one another and crowding each other's space, raising the energy of that particular stereo configuration. So less sterics is lower energy, and more sterics is higher energy. Lower energy is more stable. We've just demonstrated that E alkenes are always more stable than Z alkenes. Okay. And then the last consideration to think of when we are discussing carbon-carbon double bonds is conjugation. So this is that idea of alternating double bond, single bond, double bond, single bond, so on and so forth in a structure. So this is a heavily conjugated structure. Whereas, if you have double bonds, but they're not alternating within the structure, these are isolated carbon-carbon double bonds. There's no electron delocalization here. The more conjugation that you have, the more continuous alternating double bond, single bond, double bond, single bond, the lower the energy of that system due to electron delocalization across the pi bond system. Okay, whereas isolated carbon-carbon double bonds would be a higher energy situation.